Algebra 1 students, as we finish up Chapter 4, we have an extra section that we skipped prior to the test, so we're going to take a look at that today. Arithmetic sequences. It's a really different kind of section, but one that I actually kind of enjoy. I think you'll pick up on it fairly quickly, and in my opinion, you should do pretty well on this. Just make sure you're paying attention, make sure you take good notes, and if you have questions, ask them. Pretty normal stuff, isn't it? Alright, so let's take a look at this. Arithmetic sequences. A sequence is an ordered list of numbers that often forms a pattern. Okay, and we'll look at lots of examples of sequences as we move ahead. The terms of a sequence just represent one number in the sequence. Arithmetic means you have a difference that is constant. So you're adding or subtracting the same number every time you go from one term to the next. That common difference is what we look for. That's what we have with arithmetic sequences. It indeed tells us that we're either adding or subtracting the same thing. Now we're going to actually focus first on explicit formulas, the last definition here. An explicit formula basically writes a rule that allows you to say find the 73rd term just by plugging in the number 73. Where a recursive formula, to use a recursive, you always have to know the number that came right before that to be able to move ahead. So we'll take a look at what all that means. I think you'll pick up on it, like I said earlier, fairly quick. So to get things going here, first we have to describe the pattern in the sequence, and then we'll find the next two terms in this sequence. So the pattern I see here is 3, 6, 9, and 12. What we know is that we are doing the same thing to go from the first term to the second to the third to the fourth. We're doing the same thing each time. We're doing plus 3 all the way across. So to describe the pattern, I would say we are adding 3 each time. And the next two terms, of course, would be 15 and 18. Alright, let's do something similar on number 2. I'm looking at this one. I'm seeing that I go from 12 to 7. That's getting smaller. It's getting smaller by exactly 5. Same thing when we go from 7 to 2. And we see the same thing from 2 to negative 3. So we are subtracting 5 each time, or you could say adding negative 5. That would have the same impact. And to answer the other question, the next two terms, when you go down 5 more, you'd be at negative 8 and at negative 13. Alright, so basically we knew on 1 and 2 that they were arithmetic sequences based on the instructions that were given to us. On 3 through 5, we're trying to find out if they are in fact arithmetic. So we're going to do a very similar thing. We're going to look and see, is the change constant? 4 to 8, 8 to 12, 12 to 16. Absolutely, that's constant. And the common difference, we can just use the letter D to represent that, is 4. Alright, so let's look at number 4. We go plus 2, plus 3, plus 21. What is going on here? This is definitely not arithmetic. Okay, and since it's not arithmetic, we're not gonna find a common difference either. I know how much you guys love fractions, and because of that, I want you to pause your video and do number 5 on your own. Then hit play and see if you agree with me. Alright, welcome back. You can see my answer on number 5. It is, of course, yes. We're adding 1/3 each time, so we would say our common difference is simply 1/3. Alright, let's move onward here. Describe the 3rd, 5th, and 10th terms of the sequence described by each explicit formula. Now these are all explicit formulas. We'll look at the alternative here in a bit, but for right now we're looking at explicit formulas. And so if I want to find the 3rd term, all I have to do is this. I'll do a of 3 is equal to 4 minus 5 times 3. So then that means the 3rd term would be 4 minus 15, or negative 11. if I want to find the 10th term, I can just evaluate a of 10. So that's 4 minus 5 times 10. That's 4 minus 50. So that's negative 46. As you can see, this sequence is getting smaller. And I actually skipped one on accident, didn't I? Some of you are probably freaking out a bit that, Hale, you missed a of 5. Well, I'll get it here. It's all right. We'll get it figured out. 4 minus 25 is negative 21. All right. Let's take a look at number 7, and we'll do the same thing. The 3rd, 5th, and 10th terms. Now this time I'll actually try to do them in order, bonus. Okay, so a of 3 is going to be negative 2 plus, and then we'll have 3 minus 1 times 5. So a of 3 is, let's see, over here we do 3 minus 1, that's 2, times 5 is 10. We got to subtract 2, so it's 8. A of 5 would be negative 2 plus 5 minus 1 times 5. 4 times 5 is 20. Subtract 2, we get 18. And then finally, a of 10 is negative 2 plus 10 minus 1 times 5. That's 45 minus 2, or 43. I should point out to you, you're going to see this n minus 1 thing showing up a lot. Typically, what we see with explicit formulas is the first term is going to be this number right here, negative 2. And then we start using this n minus 1 times 5 to find all the terms that follow. So that minus 1 basically means don't add until you're on the second term, basically. Okay, so the first term is negative 2. Although you can see on number 6, I didn't have n minus 1, yet that still is an explicit formula. All right, so let's go ahead and pause the video. Why don't you guys try number 8 on your own? And now you can see my work on number 8. So the 3 terms, the 3rd term was 6, the 5th 9, and the 10th 16 and 1/2. All right, we're going to look at recursive formulas now. It's a little bit different way of writing arithmetic sequences. We won't focus just on arithmetic. You can actually use this in other ways. But a recursive sequence, got some nice fill in the blank action for you here. A recursive sequence is a sequence that uses one or more previous terms, it's usually 1, to find the following terms in a sequence. So you use the first one to find the second, use the second to find the third to find the fourth to find the fifth, etc. One of the most well-known recursive sequences is the Fibonacci sequence. If you have a few minutes, read about it on Wikipedia or some other source. Actually started with a study in rabbit breeding. Very interesting concept. Now, the way this recursive sequence works is to find the next number, like to find this number, you add the previous 2. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 and 5 is 8. 5 and 8, 13. 8 plus 13, 21. And 13 plus 21, 34. Now, of course, that would continue on as long as you wanted it to. All right, so that's an idea of how a recursive formula. We're going to look more at linear relationships. That's not linear, but it's still an interesting one. And anytime you can discuss rabbit breeding in math class, yeah, you just have to do it. It's just one of those things. All right, so some of the notation you need to know. A sub 1 means the first term of a sequence. You'll see that a lot. A sub n is the nth term. That just means whatever term you're looking for, if it's the, or whatever term you know. And if an a sub n plus 1 is the term right after that. So if you know term 6, a sub n plus 1 would be term 7. We'll look at what that means in just a moment. I love these recursive sequences in some cases. Some of them it's not as nice. But the problems we got here, it's not bad at all. In this problem, we know a sub 1 is 5. That's already written out for us. And the pattern is to find the next number. You take the one you know, and you add 8. So all I really have to do is just work down the line here and add 8. There are the first 5 terms. Now the next one, a sub 1 is 1. That's given to us here. But this time, notice it's 3 times a sub n. So I'm going to take the previous number and multiply by 3. Checking those multiplication skills, huh? 1 times 3, hopefully you have that one. 3 times 3 is 9. 9 times 3, 27. And then here's the one, 27 times 3. That's so unfair, Mr. Hale. No, it's not. It's 81. All right, why don't you guys, again, pause the video and give it a good shot on number 11. This time you're doing 2 times the number you know and subtracting 2. Go. All right, you can see my work here. And what I've done is I've written a sub 1 just as it was. To find the second term, I did 3 times 2 and subtracted 2. That gave me 4. 4 times 2 is 8, minus 2 is 6. 6 times 2, minus 2. And 10 times 2, minus 2. And we could continue going. The next digit would be 34, then 66, and so on. Kind of an interesting little sequence. All right, last slide we're going to look at here. We're actually going to kind of work backwards and write the recursive formula. And what we have to think about here is, well, what's happening when I go from one term to the next? Well, look at this. This is minus 3, minus 3, minus 3, minus 3. So I would know, for instance, that a sub 2, actually it's already listed. I don't need to write it again. We're subtracting 3 each time. So if I want to find the next term in the sequence, I take the one that I know and I subtract 3. Let's take a look at 13. Now this sequence is a little different. This time we're actually multiplying. It's times 3, times 3. And that pattern would continue all the way across. We know a sub 1 is 2. And you have to write that when you write a recursive sequence. You have to write what a sub 1 is. To find the next term, we know that we would take 3 times a sub 1, or excuse me, a sub n. It's always the previous term, a sub n. All right, why don't you guys give the last one a shot, see if you can figure out that pattern and write the recursive sequence. All right, folks, welcome back. You can see my work on number 14. You can see to go from the first term to the second, or second to third, third to fourth, etc. You're dividing by 2 each step. I wrote it as multiplying by 1/2. It works either way. You can see the sequence. Folks, work hard on this when you come back to class. Make sure you have those notes filled out. You guys have a spectacular